Back to Quantify.net. Today we are tackling a big topic in AP chemistry, which is isotopes and nuclear chemistry. So for this, we will start with the basic of what isotopes are, and then work our way up into the nuclear stability curve, radioactive decay types, half-lives, and even how to connect these to real-life nuclear power plants and medicine. By the end of this video, you'll not only understand isotopes, but also be ready to handle the nuclear chemistry problems that show up on your AP exam. Beginning. Every atom of a given element is defined by the number of protons it has in the nucleus. That number is called the atomic number, and it's what places an element on the periodic table. So, for example, hydrogen only has one proton, helium has two, lithium has three, and so on. If an atom doesn't have the right number of protons, it just cannot be that element. That's the basic rule of chemistry. However, here's the twist. While the number of protons are fixed, what isn't fixed is the number of neutrons. Neutrons are neutral particles that live in the nucleus alongside the protons. And when atoms of the same element have the same number of protons but a different number of neutrons, we call them isotopes. So here I draw carbon. So carbon 12 has 6 protons. Carbon 13 also has 6 protons. And carbon 14 also has 6 protons. This essentially is what makes them carbon. And however, carbon 12 only has 6 neutrons, 13 has 7, and 14 has 8. All of them are carbon because they have 6 protons, but their masses are different because neutrons add mass. And that's really the heart of isotopes. They're the same element, just different versions. So now that you know that different carbons have different masses. Now, if you watch the mole video, you might now wonder, if carbon had 3 isotopes, why on earth does the periodic table list its atomic mass as 12.01? That's because the periodic table doesn't show the mass of just one isotope. It shows a weighted average based on how common each isotope is in nature. Carbon 12 is about like 99% of all carbon. Carbon 13 is about 1%, and carbon 14 is so rare and radioactive that you just cannot find it. So when you average all of those together, you get 12.01. That's why atomic masses on the periodic table are just decimals and not whole numbers. They reflect the natural abundance of isotopes. Here I listed a problem here. Um, for this one, I meant this is atom Y, not a real atom, but just for a placeholder. Here you can see that there's Y, there's various types of Y here. There's Y20, Y92, which has about 15% abundance. There is Y94, which has almost 10% abundance. Y95, which has also 15% abundance. Then you have Y96, also about 15%. You have Y97 with the 10%. Then you have Y99 with 23%. And then you have Y100 with 10%. So what you would have to do here is you have to calculate all of these, such as so relative abundance would be 0.15 times 92 plus 0.1 times 94 plus 0.23 times 99 plus 0.15 times 95 plus 0.15 times 96 plus 0.1 times 97 plus 0.1 times 100. And then your answer would be the average mass. So here we can derive a formula that the average atomic mass equals to the sum of the percentage of relative abundance times the atomic weight. Well, it's not really a percentage, but just relative abundance times the atomic weight. And that's how you would find the average atomic mass. So now let's do a problem from here. Here it says based on the mass spectrum of atom Y, which of the following is false. So here you have, this is the problem I just showed. So here A lists peak D comes from an atom with 4 or more protons. Then the atom that gave peak B, so you can see peak D, this is Y100. And peak B would be Y96. And since we have a Y92 as well, we know that these are from 4 neutrons, not protons. With 4 more protons on the atom that gave peak B. So since asking for which one's false and you know it's A, let's check B, C, and D. B, peak A and peak D come from atoms that have the same number of electrons. No, electrons have nothing to do with mass spectrometry. There are 7 isotopes of atom Y. Let's count 1, 2, 3, 4, 5, 6, 7. That's true, but they're asking for false. And peak C comes from the most abundant isotope of atom Y. C is over here. C comes from the most abundant isotope of atom Y. That is also true, so this one's also false. So yeah, the answer for this one would be A. Now let's look at nuclear decay. In chemistry, you will need to know 3 types of decay, and 2 of them have actual formula change. And these 3 are alpha decay, beta decay, and gamma radiation decay. So let's first take a look at alpha decay here. Alpha decay is basically when the nucleus emits an alpha particle, which is 2 protons and 2 neutrons. And so it basically spits out a helium-4 nucleus. So usually when you take the college board exam, they will write it as helium and not as alpha particle, but they will mention alpha radiation. Here I wrote a popular example where uranium-238 and 92 loses 4 of its protons, and sorry, not 4, 4 of its particles, 2 protons and 2 neutrons, and then it turns to thorium and creates a helium isotope. So that's how this reaction works. The mass number decreases by 4 and the atomic number decreases by 2. In beta decay, which you will see here, beta decay, in beta decay, a neutron turns into a proton and then it releases an electron. The electron is called a beta particle. Here is another popular example of carbon-14 as a beta particle. So carbon-14 gained then lost a neutron and gained a proton. So that's why its atomic number increased. And then it's just spat out a electron. Sorry, this should be N. neutron. Sorry, nitrogen. So carbon turned into nitrogen and spit out an electron. Next, we look at gamma decay. Gamma decay, you don't have to worry anything about because gamma decay just means that it's just used to stabilize a radioactive particle. It doesn't have any structural change to it at all. Now, so far we have now covered half of Unit 1 of AP Chemistry. It was not really that hard. So next time we are going to cover ionization energies, isoelectronics, and then we're going to cover empirical formulas and electron configuration. See you next time, and don't forget to like and subscribe.